All right, so yesterday we introduced this idea of differentiation, and we did it via first principles. But of course, to differentiate everything via first principles each time, pain in the neck, to be honest. But that's the thing. It's a formula, so it lends itself to shortcuts. So let's just break it down. If we have a function, y is some constant value, well, we should know the answer to this anyway. Because remember, the derivative is measuring the slope of the graph. Y equals some constant value. What's the slope of the graph going to be? Okay, well, let's just prove it using first principles. So function x would be a constant. Function x plus h, also a constant. So when we sub it into our first principles formula, we get c minus c over h, which sure enough is 0 over h. So it's 0. So anytime we see a constant number, differentiate it, going to be 0. I don't need to use first principles. I know that's going to be the case. All right, let's take it to the next level. If we've got y equals some constant times x, so we're talking about a straight line. Well, I know the slope of this line would be... So again, let's just prove that that does indeed happen. Function x, kx. Function x plus h would be kx plus kh. Put that into my first principles formula. We end up with kh on h. The h's will now cancel, and yep, we get a constant k. So now, anytime I want to differentiate some constant times x, I know I'll get the constant. Differentiate 5x, I'll get 5. 10x, I'll get 10. Negative 2x, I'll get negative 2. All right, what about x to some other power? Now, in order to do this, I need to remind you of something. Remember we had difference of two squares. A squared minus b squared, a minus b, a plus b. And then we expanded on that this year, and we said, well, difference of two cubes. It still started with a minus b, but then in the second one, there went a squared plus ab plus b squared. And then we generalised it. So a to the power of 4, we noticed the same pattern will happen. So it starts with a minus b. Powers of a then went down by 1. Powers of b went up by 1. The two powers always added up to 3 in the second one. So if ever I've got a to the power of n minus b to the power of n, we get, well, okay, well, it'll start off with a minus b. And then I'll have a to the n minus 1. Powers of a go down by 1, and then powers of b go up by 1. Okay, going to need that. Because function x is going to be x to the power of n. Function x plus h will be x plus h to the power of n. So when I sub it into the first principles, there it is. A to the n minus b to the n. A is x plus h, and b is x. So I know the top of that will factorise to be, well, a minus b, which in this case, x plus h minus x. That's just going to be the h, which will cancel with the h in the bottom. The second parenthesis then, the a, which was the x plus h, starts with n minus 1. And then the powers of that are going down by 1, and the powers of x are going up by 1. So when I cancel the h, I get a whole series of x plus h, n minus 1, and so on. But we're saying the limit as h approaches 0. So if I now sub in 0, I'm going to get x to the power of n plus 1 plus x to the power of n plus 1 plus x to the power of n plus 1 plus x to the power, and so on. The question is, of course, how many x to the n minus 1s did we have? Well, if you look back to the expansion, when it was the power of 2, difference of 2 squares, I had 2 terms in the second parentheses. When it was difference of 2 cubes, I had 3 terms. So it logically would imply I'm going to have n terms in the second ones, so I must have n lots of x n minus 1. So this creates a rather neat little formula for differentiating. All I really got to do is, whatever the power is, I'm going to put that to the front and then take 1 off the power. If I have to differentiate x cubed, it'll be 3x squared. X to the power of 10, 10x to the power of 9, and so on. Okay. Well, what about if it's a negative indice though? So y equals 1 on x. So function x is 1 on x. Function x plus h, 1 on x plus h. Again, sub it into our first principles formula. So we've got an algebraic fraction to play around with here. So let's get a common denominator. The two denominators I'm pushing to the bottom, so we end up with hx, x plus h. And on the top, I'll have x minus all of x plus h. So I have minus h, which will cancel with the h on the bottom. We get minus 1 on x, x plus h. But if h approaches 0, then we get minus 1 on x squared. Now, If you think about that in index forms and in terms of what we just proved before, it still satisfies the same rule. Because if I'd started with it and said, well, that's actually x to the negative 1, bring that power to the front, subtract 1 from the power, I get minus x to the power of minus 2, which is indeed minus 1 on x squared. So for negative indices, I can still use that same idea. Bring that power down, subtract 1 from the power. Well, the only other type of index we've seen is fractional ones. So let's see if it works for that as well. So square root of x, function x plus h will then be square root of x plus h. Put that in. Now, how am I going to tidy this up? What I'm going to do is I'm going to rationalise, but not the denominator. I'm going to rationalise the numerator. So I'm going to multiply by square root of x plus h plus square root of x. That means the top becomes x plus h minus x, which is, of course, just h, and that will cancel with the h in the bottom. And I'll be left with 1 over square root of x plus h plus the square root of x. But h is approaching 0, so I've got 1 on 2 lots of root x. So again, let's turn that into index form and see if it works. So if it was index form, I would have said x to the power of a half. Bring that power to the front, half. Subtract 1 from the power. Half x to the minus a half. Well, yes, that is 1 on 2 root x. So it works for any type of index. Fractional powers, negative powers, and of course, whole numbers as well. Okay, so let's do some simple examples then. Hey, they give us a question like this in the test. We just say, thank you very much. Y equals 7. We don't need first principles. We say, oh, well, derivative is 0. 37x, derivative 37. X to the power of 10. Oh, I think I mentioned that one before. Bring the power down, so we get 10x, subtract 1 from the power, 10x to the 9. If I've got 3 different terms, it's okay. Just differentiate each bit individually. Now, notice the 3x squared, whatever the constant is out the front, I'll just multiply it by the power when I bring it down. Because if I differentiate x squared, I know I'm going to get 2x. So logically, if I differentiate 3x squared, I'll get 6x. So this will become 6x plus 6. 2x plus 1 squared. Later on, we'll see a rule how to handle this. But at this stage, we'll expand it out. So I expand that out, it'll be 4x squared plus 4x plus 1. So differentiate that, 8x plus 4. 3x plus 1 on x squared. Going to have to change that to index form so I can use my rule. So it's 3x plus x to the negative 2. Differentiate it, so the first term becomes 3. I'll have minus 2x. Be careful when you're subtracting, because remember, it's a negative power. It's actually negative 3. And I always like to write my answer in the form of the question. So they didn't use negative indices, so I haven't used it in my answer as well. X squared root x. Well, that would be x 2.5. 2.5 is 5 on 2. So it's x to the power of 5 on 2. Take 1 off that power, we get 3 on 2. So I have 5 on 2, x 3 on 2. So 5 on 2, x root x. Now, function notation. Remember I said there's these different ways of writing the derivative. In this case, they've quoted function x as x cubed minus 3 and said find f dash 2. Be careful. Very easy to misread and just think, oh, I'm just substituting 2. But no, this is saying substitute 2 into the derivative, not in the actual function. So function x is x cubed minus 3. F dash x is 3x squared. Now, it's just like normal function notation. Substitute in 2 and I get 12. And of course the whole point of why we started this, let's find the equation of a tangent. In this case it's to a cubic at the point 1, 1. So let's differentiate 5x cubed minus 6x squared plus 2. I get 15x squared minus 12x. Remember, that's not the slope, that's the formula that will allow us to find the slope at a particular x value. So sub in x equals 1. And we get a slope of 3. We got a point, we got a slope, so point slope formula, and eventually there's our tangent. I put it in general form, so 3x minus y minus 2 equals 0. Find the points on the curve where the tangents are horizontal. That's what I was talking about yesterday. A lot of these questions, we're interested in knowing the turning points. If you think about it, that's what this is really saying. Find where the tangents are horizontal. They would be those turning points. So, all right, I'm going to have to find the derivative. That's 3x squared minus 12. Now, notice my setting out here. Something I've been having a go at you about is your setting out. Explain what you're doing. Why all of a sudden am I solving this equals 0? I explain it. Oh, well, I know the tangents are horizontal when the derivative equals 0. Let's explain why I'm now going to go and solve this equation, 3x squared minus 12 equals 0. And that gives me two possibilities, plus or minus 2. And they're asking for the actual points, so I need to work out the y value as well. So it works out to be minus 2, 16, and 2, negative 16. Now, a normal. Right? We know what a tangent is. A normal is another important line in curve sketching. And it's the line that is perpendicular to the tangent at the point of contact. So really, it's finding the equation of a normal. It's no different, but you'll need to find the slope of the tangent first, and then you can say, oh, a negative inverse, that'll be the slope of the normal. So here's a random curve. There's our tangent. The normal would be perpendicular to that. Okay, so let's find that equation of the normal. We need to find the slope. So let's differentiate 8x minus 3. So when x equals 3, that's the point we're interested in. We come up with a value of 21. That's the slope of the tangent. So therefore the slope I want is minus 1 on 21. Point slope formula. Ooh, 21 times 29. That's a big number. And there we go. Okay. So 7C, 7D. The reality is you wouldn't use first principles. In a tested course, they might ask you to use first principles because they're going to want to see if you do know the technique. But we very rarely use first principles. Only maybe the first time we see a type of function, just so we can work out how to differentiate it. But once we've got the rule, it's just quicker to use the rule. That's all for today.